Welcome to our explainer covering case studies on volcanoes and earthquakes, where we'll be reporting on the latest incidents. Let's start with the pretty fundamental, unyielding truth about the ground beneath our feet. It is never truly still. Earth scientists basically operate as high-stakes detectives, constantly tracking our planet's dynamic, immense, and sometimes violent terrestrial movements. For centuries, humanity was totally at the mercy of sudden geological shifts. We relied on fragmented eyewitness accounts to desperately figure out why the Earth was shaking or why a mountain was suddenly venting choking ash into the sky. But over time, that investigative process has completely transformed. Today, we've evolved from those initial historical observations to an incredibly sophisticated network of real-time tracking applications. By pairing foundational fieldwork methodologies with live, hard data flowing in from organizations like the USGS, we can now paint a precise, up-to-the-second picture of terrestrial hazards exactly as they happen.
So let's take a quick look at how our tracking methodology has actually evolved chronologically. We can start all the way back with Persian seismic records dating back to the Assyrian period in the 13th century BC. These early eyewitness accounts were our very first real data points for understanding recurring fault activity. Fast forward a bit to 1847 and we see a massive leap in geological detective work. A scientist named Babbage conducted an archaeological displacement analysis at the Temple of Serapis in Italy. By looking closely at marine molluscan borings on the temple's columns, he realized the ruins had completely subsided into the sea, and then were gradually uplifted by invisible tectonic forces. Finally, jumping to the modern era, in 1979, researchers started using laser tracking of near-Earth satellites to measure the actual distance between points on opposite sides of the San Andreas Fault. This let them estimate plate boundary motion, which, fun fact, usually moves at about the same speed your fingernails grow.
All right, moving on to Section 1. Earthquake tracking techniques.
When you've got faults with vigorous activity, they're incredibly tempting subjects for direct gauging. Today, scientists use devices like wire-type creep meters to physically measure the millimeter-by-millimeter slip across an active fault line. We also rely heavily on electronic tilt meters installed deep down in boreholes to measure subtle crustal tilt. You do have to interpret this data carefully, though, because borehole tilt meters can sometimes get completely thrown off by heavy rainfall events and groundwater fluctuations. And to capture the massive global picture, scientists use very long baseline interferometry, or VLBI, which uses radio signals from deep space to monitor major tectonic plate boundary motion from way up above.
Which brings us to Section 2, our latest seismic incidents.
This data really illustrates the real-world application of all that monitoring we just talked about. Take the devastating magnitude 7.5 earthquake near Yumar, Venezuela. Because it was incredibly powerful and shallow, striking at just 10 kilometers, it triggered a red pager alert, meaning a high likelihood of significant damage. Compare that to the quake in Kuji, Japan. While it was still a very strong 6.9 magnitude, it happened much deeper, over 50 kilometers down, resulting in a far less severe green pager alert. And then, contrast both of those with the moderate magnitude 5.6 event in Redwood Valley, California. That one struck at a very shallow 8.9 kilometers, triggering a yellow pager alert. Our modern tracking network allows us to instantly quantify, compare, and categorize these events the very moment the crust shifts.
Now there's a stark contrast when we look at the modified Mercalli intensity, or MMI. While magnitude measures the total energy released at the source, MMI is what you actually feel standing in your living room. The shallow Venezuela quake recorded a violent level 9 shaking, literally enough to tear buildings apart. But look at the recent 4.71 magnitude event in Hawaii. That registered as a level IV, which basically feels like a heavy truck driving past your house. It's clearly noticeable, but generally non-destructive. This side-by-side really drives home why it's so absolutely crucial to measure not just the raw seismic energy, but how the ground actually behaves during an incident.
Okay, let's shift gears a bit to Section 3, monitoring volcanic deformation.
To really understand our current volcanic alert systems, we need to look back to a pivotal study published by Chadwick and his colleagues in 1983, which documented the deformation of Mount St. Helens. These researchers essentially had to deploy 5 different methods to safely track the shifting ground. They used trilateration and triangulation around the entire volcano just to monitor massive, overarching changes in its shape. They also took long-ranging distance measurements directly into the crater from a relatively safe observation spot 8.5 kilometers away. Plus, they were out there physically measuring the short horizontal and vertical distances across active, expanding cracks in the Earth. This multi-layered, highly intensive approach was absolutely essential to capture the full picture of the ground deformation as the underlying magma chamber pressurized.
And that leads us perfectly into Section 4,
the latest volcanic alerts.
Notice how impartially these alerts are categorized, based strictly on field readouts. The Great Sitkin volcano in the Aleutian Islands is currently sitting at an elevated orange watch level. That means the volcano is showing heightened or escalating unrest with an increased potential for eruption, or an eruption is already underway but posing limited hazards. Meanwhile, Shishaldin, Kuprianov, and Kilauea all remain at a lower yellow advisory level. This just means they're experiencing signs of elevated unrest above their known background levels, but they aren't displaying the rapid deformation or severe seismic swarms that would bump them into an orange or red category. It's a continuous, totally neutral, and highly structured assessment of raw geological data.
So we've evolved all the way from ancient Persian eyewitness accounts to using lasers on satellites to track live volcanic swelling. By meticulously mapping the scars of the past and tracking the incredibly subtle physical deformations of the present, we aren't just passively watching the Earth anymore, we are actively learning to anticipate its next move. I'll leave you with this to ponder. How will this continuous geological detective work ultimately safeguard the cities and infrastructure of our future? Keep exploring the data, keep asking questions about the ground beneath your feet, and thank you for joining us for this explainer.